Welcome. Today's topic is dimension reduction. So this is a technique we'll apply when we have a data set with a lot of features and we want to map each training point to a lower dimensional space. So there are several reasons why you might want to do something like this. The most immediate one for purposes of today's lecture is visualization. Also, there's some techniques that don't work very well in high dimensions, like kernel density estimation. So reducing the dimension allows us to apply those methods when otherwise they wouldn't be very effective. In some specific situations, there might be other considerations as well, like data storage. But the bottom line here is we want to take our feature matrix for our data set and map it to a new matrix with the same number of rows and many fewer columns. In problem 2, we'll start looking at perhaps the most well-known example, which is principal component analysis. And the idea is we want to be able to take, in the simplest setting, an ellipsoid-shaped point cloud like this one, and somehow use the data to extract the principal axes. So these are the axes of the ellipse that your eye is picking up here. And to formalize this mathematically, what we want to say is that first we want to choose a line which has the property that its sum of squared distances to the points is as small as possible. So that's going to be running along the primary axis. And then the other axes we'll identify by choosing lines that are orthogonal to the ones we've found so far, but otherwise minimize the sum of squared distances to the points. And this turns out to be a problem we've already solved when we studied linear algebra. The key idea is that the line which runs along the major axis of the point cloud passes through the centroid of the points. So bearing that in mind, we can simplify things a bit by just translating all the points so that the centroid is at the origin. And now this is a problem we've already solved. The line passing through the origin, which minimizes the sum of square distances to the points, is just the first column of V in the singular value decomposition of the feature matrix. Likewise, the remaining axes are going to be specified by the subsequent columns of V. So to give ourselves some confidence that this worked, what we can do is take the mean of each column. So we'll take the mean of x and we supply this keyword argument dims to say that we want to sum along the row dimension. Then we compute the SVD and then we look at the first column of V. And to give these line segments lengths, which are proportional to the axes of the ellipsoid, we'll multiply by the square root of the corresponding entry of sigma. So we'll draw an arrow from the mean to the mean shifted by this vector that we're claiming runs along the main axis. And what we see is that this checks out. It runs directly along the axis as we expected. And we can draw the other two axes in to confirm that those work as expected as well. So the green one is the second principal component and the purple one is the third principal component. And we'll note here as an aside, if we want to compute the coordinates with respect to this new basis, these principal components, then we need to take our original vectors and multiply them by V transpose. And that's just because to compute the coordinates, we just dot with these corresponding unit vectors. For example, to compute the coordinates of this point, we would dot with the unit vector running in the orange direction, the unit vector running in the purple direction, and the unit vector running in the green direction. And each of those dot products would give the corresponding coordinate. And multiplying by V transpose just organizes that process. It takes the columns of V, and because they're transposed, they're now rows, and they're poised to dot whatever vector V transpose is hitting on the right. So I want to take a minute to look at this figure from the course cheat sheet because it's a good way to get a different perspective on principal component analysis. So here we have the principal components of the MNIST training set, and each of those components is a 784-dimensional vector. But it's helpful to reshape that vector back into a 28 by 28 array and visualize it as an image. And it's not going to be grayscale anymore because some of the components might be negative. So what we do is visualize it with positive values indicated in red and negative values indicated in blue. And pixels which are black are close to 0. And we see the second one is actually pretty cool looking. And what these images are doing to try to distinguish points is dotting with the pixel intensities to give a resulting value. For example, we can see that this red actually looks quite a lot like a 0. And we would expect for most zeros that are sort of reasonably well centered, they're going to overlap a lot with this red region. So when we compute that dot product, we're going to get zeros from this black region, but we're going to get a lot of positive values from where these red positive values hit the high pixel intensity values of the 0. And typically there won't be so much of a stroke in the middle, so none of these negatives will get picked up, so you'd expect to get a big positive value. Likewise, we would expect 1 digits to pick up a lot of this blue where it's negative and not as much of the red, so they're going to end up with a negative value. So we'd expect that this first principal component does at least a great job of splitting zeros from ones, even though it wasn't designed for that. It looked at all of the digits just on the feature matrix side without seeing any of the labels. And this is the particular collection of values of positives and negatives that, when dotted with the training set, give the biggest variance. And this is exactly what we see. We have the zeros in this light blue color, and they're indeed far to the right, indicating that they're dotting with these red values to give a big positive value. And the ones are heavily concentrated here to the left of x equals 0. So that's telling you that indeed ones tend to pick up more of this blue than the red and end up to the left of the origin. The second principal component is maybe harder to see what's going on, but, well, it's a little tricky to say because the 2's probably pick up quite a bit of that red, but then they're also going to catch some of this blue, a lot of them. It would only be if that bottom stroke was way down here that a 2 would actually only catch these red pixels. So generally the 2's hopefully are close to the top, but it's not as clear cut. Likewise, maybe 7's come through and grab quite a lot of this blue, but then who can say, because maybe some 7's would come along here and then through this red region and pick up a bunch of blue and red and end up being closer to 0. If we look at the digits that are very low over here, the clearest one is maybe purple, which is 3. Actually makes a lot of sense. These blue regions look kind of like a 3 if you squint, and if you imagine sort of a prototypical 3 coming through here, it's going to pick up a lot of blue from all 3 regions. It's also going to swing through some of this red, which is going to cancel that out somewhat, but on balance it ends up sort of mostly negative. Of course, there are going to be exceptions. There's some purple points way up here. And in general, this projection of this big 784-dimensional ellipsoid, it doesn't do a fantastic job of separating out the points into different clusters. Just these like brown and greenish colors are really mixed up here, and the pink is like all spread out through the middle. So it leaves something to be desired in terms of enabling us to classify digits, but it does maybe give a glimpse of how the data is structured. So in this problem, we'll visit a blog post where there's some very nice visualizations of various dimension reduction methods. And in particular, we're going to look at a graph visualization. So the idea here is that we take all of the points in the original feature space and we compute all of their pairwise distances to each other. And for each point, we compute its 3 nearest neighbors in that data set, and we make a connection between the 2. We treat those connections physically as springs, and we also make the particles repel one another. So we put the points down in a much lower dimensional space, like in this case a 2-dimensional space, and then we let their locations evolve according to the laws of physics based on these spring connections between nearby points and the electrostatic repulsion that comes from the charge. What we see is this algorithm does quite a nice job of discovering some structure in the data set. For example, these red points end up close together. In this case, they represent handwritten 0 digits, and these green points end up close together. There's no exposure of the classes to this algorithm at all. This is purely happening on the feature side. So it's telling you that there's some sense in which there's some geometric relationship connecting, let's say, all these 3's in the 784-dimensional pixel space that these digits live in. There's also a 3D example on this web page, so you can see how the algorithm works when we're reducing to 3 dimensions instead of 2. So the only difference here is that the physics simulation happens in 3 dimensions. But you can see the edges really clearly here connecting points to their nearest neighbors. So one thing you can see is that there are sometimes points that sort of end up in the wrong cluster, like this blue one really close to all these yellow ones. And in this case, the yellow ones are 1's and the blue one is a 6, but that's a very funky 6. It does look pretty reasonably like a 1. This is a counterexample. This is a 4 that's amongst some 1's, and it really looks like a solid 4. So it's not a perfect visualization, but it is helping you discover some structure in your data set. So in problem 4, we're going to develop a sort of variation on this idea, where instead of just finding the several nearest neighbors and making connections, we're going to describe the neighbor structure in a smoother way. So suppose we have just 4 points. So this is a 4x2 feature matrix. And we want to describe the neighbors of, let's say, this point. What we're going to do is put a Gaussian centered at this point and find the values of that Gaussian at each of the other points. And give them a neighbor score, which is just proportional to that Gaussian value. And we'll normalize it to make sure that the sum of the neighbor scores is 1. So each point will have a score which says how neighborly it is to this point compared to the other points there. And if you think about it, what's going to happen is if sigma is really small, we have this really tight Gaussian here. It'll have some small value at this point, but an extremely small value at each of these 2 points, especially this one. And so the neighbor score will be heavily concentrated on this neighbor and not very much on these other 2. Whereas if we have a larger value of sigma, like a very large value of sigma, then all three are pretty much equally close. They're going to all be very close to the top of that Gaussian because it's going to take a very long time for the Gaussian to kind of fall off and begin to decay. So if we do this computation, we'll see that that's what happens. We get 0.9996 for the neighbor score of this first point when sigma is equal to 0.25. And by the time sigma is 100, we get all the way down to 0.333. So that's very close to a third. It's saying all 3 points are equal. So they'll all get pretty high scores, and then we divide by the sum of the scores, and each one will be about a third. So if we want, we can add a heat map to this picture to see it in a little more detail. So you can see when sigma is 0.25, pretty much all the value is here, and so even this value is quite small. And as you increase sigma, say it's 0.5, it's bigger, and it's a little more equitable to these 2 points. And if it's like 3, same idea. If it's like, let's say 30, then it's starting to be really pretty even-handed with these 2 points, and even giving some mass to this point, although it's hard to see from the color here. With 100, it's really spread out very diffusely. So here we have a figure we can manipulate to adjust the value of sigma and see how the scores adjust. So again, with a very small value of sigma, it's concentrating more and more on these 2 points. At 0.25, with the round off, it looks like it's just all this one and none of the other two. And then as we increase the slider, it becomes more equitable. And I maxed it out at 3 here, and here this has about 1/6 of the mass, and this has, each of these are almost equal with about 40% each. So problem 4 asks us, what will the neighbor scores be with respect to the point 0, 1? So instead of measuring with respect to this point, let's measure with respect to this point. And it says when sigma is small. So when sigma is very small, what we're observing is that these 2 points have equal distance. So they're definitely going to get the same score, and this one's going to get a very small score. So it's going to be about 1/2, 1/2, and 0. And that's what we see. This value is 0.5, this one's 0.5. A point is not a neighbor at all of itself. We force that to be 0, and then this one is extremely close to 0. So there's some wrinkles that are thrown in to make this thing work better. For example, the sigma value, it happens to turn out to be helpful to choose for each training point separately. And we'll have to do this dynamically to achieve some uniformity. And what we'll do is we'll fix a particular parameter, which is going to be a hyperparameter of the model that we can adjust to try to get different results. And we tune each sigma in such a way to get the perplexity, so that's this expression. You're summing p log p over all the neighbors, then multiplying by -1, and then raising 2 to that power. And the idea is we want to choose the sigma value that makes this equal to this particular predetermined constant that we chose. Let's see how that works in the context of this data set. So we can define a function called rho, which is the conventional letter for perplexity. So we're going to compute with respect to the j equals 1 point, and we're going to get these p values. So it's going to be px ij sigma for I from 1 to 4. And we want to take out the jth entry. And then we'll just do what we're told. 2 to the minus sum p log p. And then we'll plot that. So we see that the perplexity goes up as we increase sigma, and we can set some predetermined value like maybe 2.25 and just choose whichever sigma value corresponds to that. So in this case that would be about 1.7 or something. So we do this separately for each point. We tune the sigma value to get this distribution of neighbor scores at kind of a good place where it's not too concentrated on just a few very close neighbors, but it's not too spread out across all the neighbors. Okay, so the last thing we'll need to do is figure out where the points actually go in the image space. We're calling the locations of the image points x tilde1 up to x tilde n. And we're going to be measuring neighborliness over on the image side using these quantities called qij. So j is the point we're measuring neighborliness with respect to, and I is going to range over all of the other points. And the point is that the neighbor score should once again depend on the distance between the 2 points. But this time, instead of using a Gaussian function, we're going to use this Cauchy function, 1 plus the square, all reciprocated. And then just as we did before, we normalize those scores across the I values so that we get a total neighborliness of 1 for each point j. And using this heavier tail distribution is the key thing that really makes this work well. And the reason is that points that are really far apart, that are supposed to be close, are going to get more information about how to get closer with this heavy-tailed function than they would with a function like the Gaussian, which is practically equal to 0 outside of a neighborhood around the origin. And then finally, once we get these neighbor scores on the image side, these qij's, and we have the neighbor scores in the original space, these pij's, we compare them using this p log p over q quantity. So we sum p log p over q over all the distinct pairs, And this is using something called the KL divergence. But we don't have to get too far into the details here. The main point is that it's just measuring a discrepancy between P and Q. So whenever Pij and Qij are equal, this ratio is 1, and we take log of 1, and that gives 0 to the loss. And when they're quite different, we'll get a non-zero contribution to the loss. And this P out front is essentially weighting these contributions based on how large Pij is, the neighborliness of I with respect to j. So here we have the original locations of the points. And we're not even reducing dimension here. We're going from dimension 2 to dimension 2, but it's still non-trivial actually, because we're measuring neighborliness over here with the Gaussian and over here with this Cauchy function. And so we do actually get different values even if we start in the same places. And notice here that this distant value gets a bit higher score. That's reflective of the tail of this function being heavier. So anyway, we can adjust the images of these points. So we're just freely controlling where these 4 points go. And these 4 are set in stone. Those are our original feature values. Like we can make this point go up or down. That doesn't change very much. We can move it out and that'll get its value to kind of a better place. Like here it's 0.051, so it's exactly right to the precision we have displayed on the screen. But now these points are not balanced well. It should be 0.5 versus 0.43, so maybe we move this orange point back in. Maybe move it down too, just to kind of help with the visual. Now that's looking pretty good, and you can see the loss value is quite low compared to where we started. But notice also that we threw this one out of kilter because these neighbor scores are being normalized to add up to 1. So when we adjust these values, it does change all of them. So let's move this one back over. 2.051. So this one is just right. Now this one is slightly too small. Just a little bit closer. So that's pretty great, and to the precision displayed on the screen, we're getting a loss of 0 here. Again, if you make this go way wrong, then the loss goes up. So that's an empirical indication that this loss measure is doing something at least somewhat reasonable. So in summary, we learned 2 techniques. Principal component analysis, which identifies the axes along which the original points have the greatest variance. Or in other words, the line with the minimum sum of square distances to the points, then the line orthogonal to that with the minimum sum of square distances, and so on. And the way PCA is computed is that we shift the points to center them at the origin, then compute the singular value decomposition of the resulting matrix, and then take the first so many columns of V. Lastly, we learned about t-SNE, which aims to preserve the neighborhood structure, so it optimizes directly on the images of the points, and it encodes the neighbor structure with this function Pij. So I and j are indices of the matrix. They're different training points. Sigma is a parameter that's going to be adjusted, and the neighbor score of one point with respect to another is dependent on how far apart the points are. And we use this proportionality symbol because we're going to normalize all of the neighbors of a point j to have a total neighbor score of 1. But otherwise, the neighbor score is just going to depend on the value of this Gaussian-shaped function centered at the point xj. Then we're going to tune sigma for each j to fix what's called the perplexity of the set of neighbor scores for that j. And the idea is we want to avoid concentrating the neighbor score too much or spreading it out too much. And lastly, we apply gradient descent to the image locations with the goal of maximizing the similarity of these Pij values with Qij, where Qij is proportional to this other function of the distances between the images. On a real data set, the optimization process looks something like this.